Good morning. Welcome back. In this class, we're going to talk about two sample tests. And we're going to learn two sample tests for the mean mu, which is the mean. We're going to learn two sample tests for the variance and we're going to learn two sample tests for proportions. Okay. All right. Well, let's look at what kind of tests we're talking about. We'll look at a paired t-test, so paired differences. This will be called paired t-test. We'll look at comparing different means using independent samples. And for there, we will have two different tests. One called the two-sample t, two-sample t-test, and the other called pooled t-test. We'll also do tests on proportions. Okay, so two proportions test. Again, using the z-distribution. And we'll also do two variance test. Okay, so two variance test. Okay, so starting off, we want to start with paired t-test. Okay, so think of one sample t-test that we learned, but now we have two different data sets. Okay, usually there will be pairs in this kind of setup. So for a paired t-test, you have to get data sets that come in pairs. Let's say you're comparing two twins and their GPAs, and you get multiple different twins and you compare their GPAs. Okay, or you're comparing something that happened to an individual before a test and after a test. Okay, so paired t-test is what you will use in those cases. So you get one sample of unit, and then after a while you get something after. Okay, so you want to use the same individuals and get results for one process versus the results from another process. Okay, but the very important assumption is that it is on the same individuals. Okay, so it eliminates any differences in the individuals themselves. So you're just comparing pairs. Okay, so key assumption is dependent samples. Okay, the key assumption is dependent samples for a paired t-test. Okay, so your hypothesis is actually placed on a mu difference. Excuse me. Okay, so your hypothesis is actually placed on a mu difference. And that difference is actually the difference between mu1, which is of sample data set 1, minus mu2. Okay, so mu1 is the mean of population 1, and mu2 is the mean of population 2. Okay, then if we define d bar, or you can also call this x bar of d, also called that x bar of d, and we define standard deviation of those differences, then we can get a data set for each one of the differences and then compute the mean of it and the standard deviation of it. Okay, so for example, you have a data set for weight of students before and after working out. Okay, so you have before and after. And let's say you have a bunch of different values here. These are not zeros, I'm just not filling in the values. I don't know, they could be 110, 130, 140, etc. Right? A bunch of different values before, and then you have a bunch of different values after, 95, 110, and so on. Okay? Then you can create a difference column, okay, which is going to be the difference between the first number and the second number. So what was happening before and after, because they belong to the same individual, right? It's dependent. So for the first case, it'd be 110 minus 95. Okay, 15. Then for the second one, it'd be 130 minus 110, right? So 20. And you would do this for all the different data values. Based on that data set, then you can find out the average of those differences. You can also denote it d bar, right? Which is going to be the average of differences. And you can also, from that data set, find out the standard deviation of that data set, SD. Okay? This is just one sample of data. So from there you can find out its mean, and you can find out its standard deviation. Then you can construct a confidence interval and perform a hypothesis test. And in that confidence interval, you know, if you denote it x bar of d or d bar, whatever you like, it's going to be that plus or minus t critical, right? Which we said was alpha by 2 in the confidence interval chapter, times by the standard error of the difference, the standard deviation of the differences, divided by square root of n. That gives you the confidence interval, right? And that t critical is obviously dependent on degrees of freedom, and the degrees of freedom for a paired t-test degrees of freedom for a paired t-test is n minus 1, right? Note that for paired t-test, n1 equals to n2 equals to n. It's just all the same number, right? Sample size, they have to be in pairs, right? So for paired t-test, the degrees of freedom is going to be n minus 1, and that n is the sample size of the population 1, which is going to be the same as the size of from population 2 that you collect. Okay? And just like a confidence interval, we can also compute t statistic. Okay? If you call it denoted by x bar of d, that's also fine, minus what you assumed the difference to be. So if you want to denote it as mu difference, mu d naught, that's also fine, as sd divided by square root of n. Right? That's the same thing here. So average differences minus the hypothesized difference. right? Your hypothesized difference is the same way that you write a hypothesis test. So you could write this as mu difference equals to mu d naught versus h1 mu difference not equals to mu d naught. Or you can also choose to write this as h naught, that says mu difference is equal to some d naught, and mu1 is mu difference not equals to some d naught. And again, you can also have one-sided hypothesis, that in the form of greater than or less than. Okay, and therefore you end up with that hypothesis. Mu difference is equal to mu d naught, or it being greater than or less than or not equal to. Notice here now, instead of putting mu d naught or just d naught, we're using 0. Why is that the case? Well, typically we're trying to see if there is a difference between population 1 and population 2. And to test for if there is a difference between the two, well, then you can just test for if the difference is 0, or if the difference is not equals to 0, or positive or less than. Okay, and so theoretically or conceptually, you'll see that this test is pretty much the same as doing a one-sample t-test. Okay, so let's look at an example. Individuals are diagnosed as caffeine dependent, are deprived of caffeine-rich foods, and assigned to receive daily pills. Sometimes the pills contains caffeine, and other times they contain a placebo. And you're trying to measure depression. You have the same 11 individuals. Okay, so 11 people were selected, and you have the same 11 people who had it with caffeine and who had it with placebo. That's very important. Dependent samples. If it was different individuals here for sample 1 and different individuals for sample 2, then we couldn't use this test. Okay, so dependent samples. Okay, and N1 equals to N2, which equals to N, which equals to 11. Okay, all of them are the same size, 11 people in each, the same 11 people going through the tests. Okay, and therefore we created a column of data for the differences. So this is all your differences. So this is D1, D2, D3, and so on, all the way down to D11. And you can see there could be negative values in there too. Okay. You look at the data set and it looks fairly normally distributed. Okay, so we can test using a two-sample t-test, or paired t-test in this case. Right. And then we find the average. So the average, this is d bar, or you can call it x bar d. That's 7.36, which is the average of these values. And the standard deviation of the differences is the standard deviation of these values. Then we can write the hypothesis as mu difference equals to 0, or mu difference is positive because we're testing for if placebo had a bigger impact than caffeine. A question actually had asked for if placebo had a bigger impact than caffeine, if the numbers were expected to be positive. And then you compute T-stat, right? So T-stat is equal to D bar. And again, this number is typically going to be 0. So D bar divided by S over square root of N. And D bar is the average of these numbers, which we found out to be 7.36, divided by standard deviation, which we found out to be 6.92, and the sample size was 11. If you work this out, you get 3.53. Okay, and then you go to Minitab, and you find p-value. All right, so back to graph, probability distribution plot, view probability. Here we have the t-distribution, right? We're doing a paired t-test. What's my degrees of freedom? Well, my sample size was 11, so my degrees of freedom is 10. Right, and I have the t-value, and I'm checking for it for a right-hand side, right, because it's greater than. Our hypothesis was it's greater than 0. So our t-value is 3.53. And we click OK, and we get the probability, 0.003. Okay, we get the probability of 0.003, which is less than equal to alpha, which means reject H naught. Okay, and therefore we have proved that caffeine deprivation causes a significant increase in depression. Okay, so basically the same rule that we did for a single sample test will exactly apply to a two sample test. Okay, just like comparing t-stat with t-critical, you can do the exact same thing. You can compute t-stat, compare it with t-critical, or you can compute p-value and then compare it with alpha. And then you compute t-stat using this equation, right? And your degrees of freedom is n minus 1. Your H naught is mu d is equal to some value, and H1 is mu d is not equal to some value. And these values typically is 0. D0 equals to 0. Okay, now I want you to do a quiz. Measuring the body fat percentage before and after a soccer game, literature says there is no difference between the two. You take a sample of 5 soccer players before and after the game. Before you have the following percentages, after you have the following percentages. Based on a significance level of 0.05, is there a difference in body fat percentages before and after a game of soccer? So perform the test here. Right, make sure you state your hypothesis. Write the name of the test. If you're going to use Minitab, show the output. And also construct the 90% confidence interval. Okay? Construct the 90% confidence interval and tell us what it means. When you do the confidence interval, tell us what the confidence interval means in terms of difference in body fat percentages. Again, you can find this quiz on Canvas under the assignments. It's going to be right after this video, posted in your modules. It's already posted there, but it's going to be sequentially placed after your after this video in that chapter. So make sure you complete it by the due date. When we're dealing with independent samples, okay, then the question becomes, is the sample that we have, the two samples that we have, are they from the same population or are they from different population? Okay, so that's why we set up a hypothesis test. Excuse me. That's why we set up a hypothesis test that tests for, is the average of the two populations the same as in this case, picture B, or are my samples really from two different populations, as in picture A? And that's what we're testing for on independent samples. Okay? Note that for dependent samples, we already covered that. That was paired t-test. Okay, so for dependent samples, we did paired t-test. But all of this that we're going to discuss from now on assumes independent samples. Okay, independent samples from here on till end of chapter. Okay, so that's the question. That's what we want to ask. Now, when we know sigma 1 and sigma 2, okay, when sigma 1 or sigma 1 squared, variance of 1, and variance of the two different populations are known, then we want to use a two-sample z-test. Okay? We want to use a two-sample z-test. And for that, we can compute z-stat using this formula. Okay, so it's x bar 1 minus x bar 2. So the mean difference between the two means minus the hypothesized difference. So our H naught is that these two things, these two means are the same, and our H1 is that they're different. Well, this can be written as, okay, so same as mu1 minus mu2 equals to 0 versus, right, so this is versus mu1 minus mu2 not equals to 0. You notice that these two things are the same and these two things are the same, right? If two things are equal, well, the difference between them will be 0, and if two things are not equal, the difference between them will be not 0. Okay. So typically we are testing for 0 on the right hand side, and so what happens is this thing can vanish. Okay, and you're left with the difference between the two sample means divided by this bottom part, which is the standard deviation on the difference of means. Okay, so standard deviation on x bar 1 minus x bar 2. Okay, you can also denote it as sigma x bar 1 minus x bar 2. This thing, from now on, we're going to call standard error. And this formula will change for different tests. Okay, this is what you use in the denominator of z-statistic. Remember, when we talked about just one of them, right? Remember, for sigma of x bar, we said that was equal to sigma over square root of n, right? For just one of them. When we have two of them, two different means, and we're looking at the difference in means, well, that standard deviation is expressed as this, and it's called the standard error. Okay, and so just like you compute z-stat, you can also compute the confidence interval. Okay, and that is the difference x bar 1 minus x bar 2, the difference in means plus or minus z of alpha by 2 times the standard error. This thing. So that multiplied by z of alpha by 2, that gives you the confidence interval. Right? And then again, just like before, we talked about in confidence interval chapter 8, this is your margin of error, m. Right? Your z value times the standard error gives you margin of error. Okay, but this is a very short discussion in all of this, and we're going to keep it very short because hardly ever will you know the value of sigma 1 and sigma 2. Okay, so this is typically unknown. So in fact, in Minitab, you'll see there is even no option to actually do a two-sample z-test. Right? In Minitab, there isn't an inbuilt function to do a two-sample z-test, because when will you ever know the variance of two different populations? Usually measuring population information is very difficult. Okay? So typically we won't use this, but it helps us understand how to do a two-sample test. Okay? So just like we did this for two-sample z-test, now we're going to talk about two-sample t-test. Right? When we don't know sigma 1 and sigma 2. Right? These are unknown. These are population parameters that we don't know anything about. Well, we always have the sample information, okay, x bar 1 and S1, which is mean and standard deviation of the first sample, and x bar 2 and S2, which is mean and standard deviation of the second sample. We can use these to estimate for the population parameters and do a corresponding test. And that test is going to be called a two-sample t-test. Okay, and the assumption there is that we have normality, normally distributed data sets. They are independent, right? Otherwise, we would have done a paired t-test if it was dependent. And no prior information about sigma 1 and sigma 2. We don't have any information. We just assume we don't know anything about the population variances or standard deviations. Okay. Okay, same thing. If they're squared, they're variances. If they're not squared, they're standard deviation. We assume we don't know anything about it. Then we can use the two-sample t-test. So to do that, we're going to use the t-distribution instead of the z, right? Note that we don't have sigma 1 and sigma 2, right? So in the z case, right, in z distribution, we said the standard deviation of the differences, x bar 1 and x bar 2, was measured as square root of sigma 1 squared over n1 plus sigma 2 squared over n2, right? This was just in the previous slide. Now when we're talking about t-distribution, in the t-distribution, we don't have sigma 1 and sigma 2. So we're going to use sample standard deviation S to denote the difference in their means as square root of s1 squared over n1 plus s2 squared over n2. Okay, so that's the standard error, right? We talked about this being the standard error. Okay, so that's what we get, how we get the standard error. Okay, and the degrees of freedom for two-sample t-test is equal to the smallest value between n1 minus 1 and n2 minus 1. Okay, so you look at the sample size of one of them, subtract 1 from it, find the sample size of the other one, subtract 1 from it, pick the minimum value between the two, the smallest one. Okay? And so based on these definitions, we can then do a hypothesis test, right, where mu1 equals to mu2, which is the same as saying mu1 minus mu2 equals to 0. Okay. And we can then set up H1, alternate hypothesis, which is to say mu1 minus mu2 not equals to 0. Or we can also have mu1 minus mu2 greater than 0, right? Or so on, right? Less than 0 as the other option. And then we can compute t-stat as the difference in means minus our hypothesized difference, which typically we test for 0, right? So this goes away, divided by the standard error. And we said the standard error is the square root of s1 squared over n1 plus s2 squared over n2. So variance of 1 divided by sample size of 1 plus variance of the other divided by sample size of the other. Take a square root of those two things, add it up, and then find the difference between the means and divide by that whole quantity. Okay, that gives us the t-stat value that we so dearly need. Okay, now once you find t-stat, it's straightforward from there. Find the p-value, right, based on the degrees of freedom. Find the degrees of freedom by finding the minimum value of n1 minus 1 and n2 minus 1, the smallest one between the two. Okay, and then using that, go to Minitab, find the p-value based on this t-statistic and the degrees of freedom. So let's look at an example. You're trying to find out if consumers have more favorable reaction to product label if they have been primed to the image beforehand. So you have two different groups that you collected. 22 people had been primed and 20 people had not been primed. The means were 4.0 and 2.95. The standard deviations was 0.93 and 0.94. Okay, we want to know whether the primed group views the product more favorably than the non-primed group. okay? And you're assuming higher the number, the more favorable you view something. So what does that mean? That means when you're setting up your hypothesis test, H naught, practice this with me, you are going to check if mu1, which is the average of the primed, you're trying to see if it's more favorable, okay, so it should be higher, is higher than mu2. And, sorry, this will be equal to, right? H naught is always equal to. And H1 is going to be mu1 greater than mu2. Right? The null hypothesis is always going to be equal to. And in the alternate hypothesis, you want it to be greater than. Notice in the alternate, you should never have greater than or equal to. The equal to is already handled for in the null hypothesis. Here, you want it to be either that says not equals to, or greater than, or less than. So this is the same as saying our null hypothesis is that mu1 minus mu2 equals to 0. And our alternate hypothesis is mu1 minus mu2 is greater than 0. Okay, so that's what we're testing for. That hypothesis. So, what's our degrees of freedom? Minimum of n1 minus 1 and n2 minus 1. Right. So n1 is 22, so that's 21. And non-primed is 20, so this is 19. So we're going to pick the smallest number, so that's going to be 19. Okay. And then we want to find the t-statistic based on the values that we have, the x bar, the s1, the s2, the x bar 2, n1, and n2. Okay, that's just plugging and chugging. 4.0, x bar 1 minus x bar 2, divided by 0.93 squared, which is s1 squared over n1 plus s2 squared over n2 gives you your t-stat. Okay. Then we go to Minitab. Okay, once we're in Minitab, we go back to the same place, probability distribution plot. You're probably getting very used to using this function now, view probability. Click OK. We're dealing with the t distribution. Our degrees of freedom we found out was 19. And shaded area, we're trying to find the right-hand side, right? It's a one-sided, greater than equal to. And our x value is what we're given, and it was 3.63 as the t-statistic, right? 3.63. Click OK, and you find the probability, it's almost 0, so 0.001. Okay, so p-value is 0.001. It's one-sided, right? And therefore, there is a very strong, significant difference between them. We reject H naught, and we find out that consumers who wear primed view the dog shampoo much more favorably. There is a significant difference. Okay, and just like you did a hypothesis test, you can also compute the confidence interval, right, on a two-sample t-test. Okay, so two-sample t confidence interval. Okay, that's straight x bar 1 minus x bar 2 plus or minus my margin of error. And we define that margin of error as t critical times the standard error that you just used previously. Okay, so this t critical times the standard error, and that's usually dependent on alpha by 2 and degrees of freedom, right? Your t critical is always dependent on alpha by 2, right? Alpha divided by 2, and also the degrees of freedom, right? In this case, is the smallest value between n1 minus 1 and n2 minus 1. Right? Using that degrees of freedom and alpha divided by 2, you can find out t critical. multiplied by the standard error right here to find the confidence interval. So for that same example of shampoo and dogs, if you want to find out the confidence interval on the difference in means, you go to Minitab, put in a degrees of freedom of 19, and find out that T critical is 2.022. I want you to try getting this value by yourself. Make sure you get it. If you don't, contact me at aroy@bgsu.edu. Email me about it, okay? I'll guide you along. So once you find the T critical, then you can find out the confidence interval, because you know the difference in means, 4 minus 2.95 is 1.05. T critical, you found out is 2.022. And then this standard error is 0.289. Once you plug in this variance, 0.93 squared divided by 22 plus 0.94 squared divided by 20 from these values, that comes out to be 0.289 once you take the square root of it. Multiply those two numbers, add it on, and subtract it from 1.05. You end up with the confidence interval being between 0.47 and 1.63. Okay, so what does that mean? This means that the difference between the two groups, the primed minus non-primed, okay, the difference between primed average minus non-primed average is positive. Why? Because 0 is not in that confidence interval. Okay, so since 0 not in confidence interval, it says there's a positive difference between mu1 minus mu2. Okay, so average shampoo favorability of primed minus average shampoo favorability of non-primed shows that there is a positive difference, i.e. there is a difference between primed compared to non-primed. Primed would have a higher value on average than non-primed would, 95% of the time, because there's a 95% confidence interval. Okay, so this two-sample T is fairly robust because you don't have to assume anything about standard deviation, and it is independent. Okay, it's more robust than most paired t-test or the next test that we're going to talk about, the pooled t-test, and so on. Okay, when you can choose equal sizes between the two different samples, that's going to make your study even more robust. You should try to pick at least sample sizes greater than 30 for each one of them. I know it says here N1 plus N2 has to be at least 40, but to be on the safe side, you should pick at least N1 greater than 30 and N2 greater than 30. Okay, so I want you to practice doing a two-sample t-test with this data set. Okay, again, this is therefore your practice with some real data. You have the management scores of two different classes. Okay. And these are two different midterms based on two different populations. So two different groups of students. For the different exams. So this is midterm 1. Okay, and this is midterm 2. You have a bunch of students with their scores in there. I want you to compare them and test for a difference in means. Okay, so test for a difference in the two midterm averages, or means. What test will you use? if you assume that they are two different groups of students, say what test statistic it is and state the p-value and make your conclusion. Pause the video here if you don't want to hear the answer, or at least steps forward. I'm not going to give you the final answer, but I'll give you the steps forward, and then you can try it out on your own. And if you have any questions, again, contact me at aroy@bgsu.edu. Spoiler alert. All right, so for running this test, we know that there are two different groups of students, so we can assume independent samples. Okay, so therefore I'm going to use the two sample t-test. Okay, and here you would report the test statistic, t-stat, find the p-value based on t-stat from Minitab, and make your conclusion whether you will reject or fail to reject H naught, and what does that mean? Okay, make sure you state up your hypothesis too, right? And I can get you started on that. H naught is that mu1 is equal to mu2, and H1 is mu1 not equals to mu2. Right? The average of midterm 1 is equal to average of midterm 2 versus they're not equal to each other. Okay, now we talk about a t-test for two different samples when we are assuming equal variance for the population, and that's called a pooled two-sample test or a pooled t-test. Okay, the one we already talked about, the two-sample t-test, right? The assumption there was we don't have any prior information about the variance of the population. Right, so two-sample t-test, we did not make the assumption about anything about their variances, right? So they were most likely not equal to. We didn't make that assumption. But the assumption for pooled t-test, okay, so pooled t-test is that the variance of one population is equal to the variance of the other population. Okay, so we have two normally distributed populations, and for two-sample t-test, the spreads will be different, one fatter, one duller, but for pooled t-test, they will be the same. Okay, and so for a pooled t-test, so degrees of freedom for a pooled t-test is equal to n1 plus n2 minus 2. Okay, that's the degrees of freedom. Now it's hard to check if the two population variances are equal, right, without knowing the actual values. Because if you knew the actual values, you would use a two-sample z-test, correct? Here, we don't know the actual sigma 1 and sigma 2, but we have to assume them to be equal, so it's hard to do that. We'll actually learn how to do this test at the end of this chapter, right? But if we can somehow make that assumption that the two variances of one sample and the other sample means that the population variances are the same, okay? Again, note that these are not sample variances, these are population variances. Or population standard deviations. right? If the population variances are the same, they're equal to each other without actually knowing their values, then we're going to use the pooled t-test. Okay? And for that, we need to use something called the pooled variance. Okay, because we're assuming that the variance of one is equal to the variance of the other, we also need to figure out a pooled variance for the sample, right? And to do that, we use this formula where it's n1 minus 1 times by the variance of one sample plus n2 minus 1 times by the variance of the other sample, divided by the degrees of freedom. You're basically standardizing the values, right? You're taking out the contribution from one of the data sets, adding it to the other data sets, and dividing it by the total size. Okay, so you're pooling, right? You put things together, you pool, right? So that's the same concept. You're pooling the variances from two different data sets to make one variance, and that's called the pooled variance. Okay, and the degrees of freedom for that is n1 plus n2 minus 2 for a pooled t-test. Okay, and based on that, you can compute a t-statistic. Okay, notice that for t-stat, for the pooled t is same numerator, but in the denominator, instead of having s1 squared and s2 squared, you bring out the sp outside, and this is pooled standard deviation, sp. Okay, and that's the square root of sp squared, the variance that you get from up here. Okay, once you find that variance, take the square root of it, find the pooled standard deviation, fit it to that formula, and you got yourself the pooled t-stat. And similarly, you can also find the confidence interval, okay, as the difference in means, just like you did before, plus or minus t critical, right, times by the pooled standard deviation, square root of 1 over n1 plus 1 over n2, right? So this whole thing, including SP, this is your standard error, right? Very similar to before. That's your t critical. So t critical multiplied by standard error. Okay, so t critical multiplied by standard error gives you the margin of error. And so the difference in mean plus or minus the margin of error gives you the confidence interval. So let's look at an example. You have two different groups of firms, one healthy, one failed. You have two different sample sizes, two different means, two different standard deviations. And you want to test the hypothesis if the two averages are the same. And assume that based on these two standard deviations, they are equal to each other. Assume that you know based on the sample standard deviations that the population standard deviations are the same. So assume sigma 1 squared is equal to sigma 2 squared. In the test, I will use very clear terminology to let you know if you can make this assumption. Okay? Either you will perform a hypothesis test to prove this and then do a hypothesis test on the means, or I will say they come from a population with the exact same variances or exact same standard deviations. And then you can assume this. And then you can use the pooled t-test. Right, so we can then find the pooled variance. Okay, find out the pooled standard deviation, just plugging in numbers. N1 is 67 minus 1, right? 68 minus 1 is 67. Plugging in standard deviation squared plus N2 minus 1 times standard deviation squared divided by N1 plus N2 minus 2. Find the pooled variance, take the square root of it, and you got yourself the pooled standard deviation. Once you find that, plug in the values of x bar 1, x bar 2, pooled standard deviation, 1 over n1 plus 1 over n2, and you got yourself t-stat. Okay. plug in tstat into Minitab, and you find out the p-value is somewhere around 0.01, and in fact smaller than 0.01. .001. There's 2 zeros. Okay, and therefore, what can we say? P-value is much less than alpha. Therefore, reject H naught. The means are very different from each other. Okay, so let's see how to do this test in Minitab. N68.3 and N68.33 X bar 1.7256 0.8236 0.6393 0.4811. Okay, so based on these values that we just got, we go back to stat, basic statistics. We're going to do a 2-sample T. Okay, if you had the data in 2 different columns, you could use that also, and you would have to put in each sample in its own column and put in sample 1 and sample 2. If you had the data in just 1 column, okay, all the X values in 1 column, and in the second column you had the sample IDs, i.e. it said 1 or 2 next to a data point showing that it came from either group 1 or in firm 1 or firm 2. Those would be your IDs. Okay, so if you had it in that format, you could also do that. But here we have it summarized. And our sample size for one of them is 68. The sample mean for that one is 1.7256. And the sample standard deviation is 0.8236. And the other one is 33. Oh, made a mistake. The 0.8236 is the mean of the other one. The standard deviation is 0.6393 for the first one and 0.4811 for the second one. Okay, if we were just doing a 2-sample t-test, then you would leave it like this. Okay, and then press OK and interpret the results. But because we're doing a pooled t-test, we're going to assume equal variances. That's the only difference in Minitab between doing a 2-sample t-test and a pooled t-test. By checking this box, you want Minitab to do a pooled t-test. So we click OK and OK. Minitab then tells you what the pooled standard deviation is. And if you notice, that's the exact same standard deviation that we got in when we hand calculated it. And that's the exact same t-value, t-statistic that we got when we hand calculated it. And based on that, the p-value is 0. Okay, and so p-value is not, in fact, not only less than 0.01, p-value is equal to 0, which is less than alpha. Therefore, reject H naught. Therefore, there's a significant difference between them. Okay, and similarly, you can also compute the confidence interval. So, how do you compute confidence interval? It is x bar 1 minus x bar 2. Remember, this is for 2 different samples, plus or minus margin of error, which is x bar 1 minus x bar 2 plus or minus t critical, which is alpha by 2 and degrees of freedom, times by the standard error. And we said for the pooled t-test, that is the pooled standard deviation 1 over n1 plus 1 over n2. Okay, and so this is your T critical, which is T of, now we're doing a 95% confidence interval, so it is 0.025, right? The 5% is divided on two sides, so 2.5% on each side. And the degrees of freedom is 100. Okay, why? Because n1 equals to, let's see what it was in the previous slide, 68 and 33. So n1 equals to 68, n2 equals to 33, right? That gives 101 minus 1 is going to be 99. Okay, but there is no difference between 99 and 100 because the sample sizes are large enough. So we just chose 100 because in the tables, if you did this by table and not Minitab, there is a value for 100 rather than at 99. And that's 1.984. If you look at 99, you're going to get the same exact t-value because when sample sizes are that large, it doesn't make a difference for the t distribution between one sample point. Okay, so 1.984, if you plug it in, multiplied by the pooled standard deviation and the square root of 1 over n1 plus 1 over n2, you get 0.25 as the margin of error. Okay, and then to find the confidence interval, it is the difference in mean plus or minus the margin of error, and that leads to 0.65 and 1.15 as the confidence interval on the difference in means. Okay, so this shows that mu1 minus mu2, okay, so firms that were healthy, the average of that minus firms that failed, the average of that is that there is a positive difference between the two. Firms that are healthy, on average, have a higher value than firms that failed. Okay, so let's run through some examples of what kind of test you would use for any of these situations. And that's really mostly what this class is concerned about, using the correct test. So you're comparing vitamin content of bread immediately after baking versus 3 days later. Here, the loaves of bread are the same that's used before and after. What kind of a test should you use? Dependent samples, right? Same loaves of bread. That's the key part. So, paired t-test. Comparing vitamin content of bread immediately after baking versus 3 days later, tests made on independent loaves, different loaves. Therefore, two-sample t-test. Average fuel efficiency for 2005 vehicles is 21 miles per gallon. Is the average fuel efficiency higher in the new generation green vehicles? So you collected a single sample of green vehicles. And you're testing H0 if mu equals to 21 and H1 if mu not equals to 21. What does this look like? This is a one sample t-test. Okay. Is blood pressure altered by the use of an oral contraceptive? Comparing a group of women not using oral contraceptive with a group taking it. Two different groups. Another group, right? Two different groups. So, two-sample t-test. Reviewing insurance records for dollar amounts paid after a fire damage in houses equipped with a fire extinguisher versus houses without a fire extinguisher. Again, two different groups. Houses without and houses with. Right, so two sample t-test. Okay, so I hope you see the picture of how to pick the correct test to run. So again, this table summarizes for you the critical value way of finding out a solution or a conclusion versus the test statistic way of doing it. Okay, let's try an example. The head of the English department is interested in difference in writing scores between freshman English students who are taught by different teachers. The incoming freshmen are randomly assigned to one of the two English teachers and are given a standardized writing test after the first semester. We take a sample of 8 students from each class, from one class, and 9 from the other. So class 1 has 9 students, class 2 has 8 students. Is there a difference in achievement on writing tests between the two classes? So what kind of a test is this? Let's decide that first. Well, there are two different groups, right? Two different students, two different teachers in each one of the different classes. They're all different from each other. So they are independent samples. Okay, that takes paired t-test out of the equation. And do we have any information about the population variances? Nothing in here suggests that, right? So we cannot assume anything, so assume that these two things are not equal to each other. Okay, assume independent samples and the two variances are not equal to each other. That means what? Two sample t-test. Okay, so H naught is mu class 1 is equal to mu class 2 versus H1 is mu class 1 not equals to mu class 2. Okay, and so let's see how to do this entire thing in Minitab just for practice. We know how to do it by hand, right? By hand, you compute t-stat, and that would be x bar 1 minus x bar 2 divided by, remember, for the two sample t-test, it is s1 squared over n1 plus s2 squared over n2. Okay, and then you would find the p-value and so on. But let's see how to do this in Minitab. So once you type in the data in Minitab, right, all the class 1 scores and the class 2 scores, we go to stat, basic statistic, and we're doing a two sample t. This is numbers from the previous example that we ran, but for this case, we have each sample in its own column, right? Class 1, class 2. So in sample 1, put in class 1, and sample 2, put in class 2. Anything in options? Well, we're just testing for if there's a difference between them. And we don't want to have assume equal variance because it's not a pooled t-test, so you have to uncheck that. Or if you got into it at the beginning, this would be unchecked automatically. That's the default setting. Okay, so make sure this is unchecked. And the confidence level is 95%. Our hypothesized difference is 0 between the two of them, right? That's what we think there's a difference or not, and 0 is what we're usually testing for. Click OK, click OK, and you got yourself the output. The most important part is your t-statistic is negative 3.5 and your p-value is 0.04. Okay, so from Minitab we get negative 3.5, and based on that a p-value of 0.04. I believe it was 0.004. See, good thing I checked. 0.004. excuse me, 0.004. Okay, and that is much, much smaller than alpha. Therefore, reject H naught. The two means are definitely different from each other. Okay, so accept H1. All right, let's try another one. A math teacher wants to determine the effectiveness of her statistics lessons. She gives a simple skills test to 9 students before the start of a class, and the same skills test to the same students after the class is ended. And she does it on these 9 students. So I'm not going to do this for you, but I will let you practice this and try it out on your own. But I will tell you what the correct approach is. And if you don't want to hear that, press pause now. Okay, spoiler alert. The test you want to run is a paired t-test. Right? These are the same students, all 9 of them, that's being tested pre-test and post-test. So they are dependent samples. Okay, and then you find the difference between them, and you can run this in Minitab. In fact, if you find the difference column here, all the DIs, each of the differences, and then put in the average from there, which is, let's say, D bar, as the average differences, and you put in the standard deviation of the differences, you can do the rest of it in Minitab. Okay, if you have any problem with that, again, contact me at aroy.bgsu.edu. Okay, now let's move on to another distribution, and this is one of the final distributions that you're really going to have to learn when we're comparing hypothesis testing. Remember, when we did a hypothesis on one variance, right, if it was equal to a particular value, right, versus if that variance was, sorry, there's only one of them, right, if that variance was not equal to a particular value, what kind of a distribution did we use for this? Anybody remember? We used the chi-squared distribution. For this. Okay, now when we're comparing two different variances, I just got the indexes flipped, but that doesn't matter. When we're comparing two different variances, for that, we have to use something called the F distribution. It's kind of like the chi-square distribution. You see how it's skewed to the right, right? It's skewed to the right, just like the chi-squared was. You know, it has only positive values. Non-negative values, right? Only positive values. However, like the chi-squared was dependent on 1 degrees of freedom, here the degrees of freedom, there's 2 different ones for the F distribution. Okay, that's because when we write this hypothesis, sorry, this is H0 and this is H1. right? Null hypothesis and alternate hypothesis. When we write H0, we can rewrite this variance as a fraction equals to 1 and as the fraction not equals to 1. Right, you notice how this is a little bit different than subtracting the two different sides and making it equal to 0. The reason we don't do that is because to say that the variances cancel out is to say that the data set is constant. Okay, so if something doesn't have any variability in it, right, they cancel each other out, that means it's just one number. Right? If there is no variance in your data set, you have only one number. Right? It's constant. So we can't really say that because usually it's not just one data point. You have a whole bunch of data points, right? And based on that, you're testing this hypothesis. So you cannot write sigma 1 squared minus sigma 2 squared equals to 0 for a hypothesis test on two variances. You have to form a ratio of them, right? Divide both sides by sigma 2 squared, form a ratio, and that equals to 1. Or it doesn't equal to 1. Or you can also have it greater than 1 or less than 1. Okay? And that degrees of freedom, therefore, there's two different ones. One that belongs to the numerator, and that's exactly from this kind of setup of a fraction, numerator, and one that belongs to the denominator. Okay, so let's dive a little bit deeper. So the distribution is very similar. You have alpha as a critical probability, right, that you're comparing it to, the test significance level, same as before. Right, and that F alpha, which is your critical value, F critical, depends on two different degrees of freedom, 1 and 2. And that is because we're talking about that ratio, right? Forming that ratio equals to 1 versus not equals to 1, or you can also have it greater than, right? Depends. Is because once we form that, our F stat is actually equal to this kind of a setup where it's the variance of one sample divided by the variance of the other sample. Okay? Now you could also flip them. So how do you know which one to put on the top? Right? Which variance goes on the top? Right? That should be the question you're asking. Well, it's always the larger of the two different variants that goes on the top and the smaller of the two different variants that goes on the bottom. Okay? And then the degrees of freedom corresponding to the larger of the variances goes in the numerator, and then the degrees of freedom corresponding to the smaller variances goes in the denominator. Okay, and then it's just a table which is going to Minitab, finding out the probability, and finding a p-value. Okay, so you set up a hypothesis that says sigma 1 squared equals to sigma 2. And sigma 1 squared not equals to sigma 2. Or you can have it one-sided. And then you have to normalize, i.e. form a fraction, sigma 1 squared over sigma 2 squared equals to 1 versus greater than 1 or not equal to 1 or less than 1, right? And then you reject h naught if that fraction is very far away from 1. Okay, so what is very far away? It depends on the p-value. Right, so let's look at an example. A data set contains 480 ceramic strength measurements for 2 batches of material. Okay, that batch 1 has 240, N1, and N2. The mean x bar 1 is that value, and standard deviation S1 is that value. X bar 2 is that value, and S2 is that value. You want to test the hypothesis if the two variances are the same or not, right? Which is to say sigma 1 squared over sigma 2 squared equals to 1 versus sigma 1 squared over sigma 2 squared not equals to 1. Okay, then I can find F stat. As S1 squared over S2 squared. Plug in the two values, right? The larger standard deviation squared divided by the smaller standard deviation squared, you get 1.12. And when you go and find the p-value, you get 0.3704. The degrees of freedom for both of them is 239 and 239. Okay, since p-value is greater than alpha, we fail to reject H0. That means test is inconclusive. Okay, so let's have a look at how to do this in Minitab, the whole thing. Okay, so we're doing a hypothesis test on two variants. So stat, basic statistics, two variances instead of one variance. Okay, we have it all summarized. And it's summarized in terms of standard deviations, I believe. Yeah, there are standard deviations given to you. Okay, so I click sample standard deviations. I have to put in sample size. Remember, that's 240 for both of them. And then I have to put in the standard deviations in the data set. And so one of them is 65.54909. And the other one is 61.85425. Okay, and in options you can change it, but we're checking exactly ratio equals not equals to, right? It's a two-sided, and the hypothesis ratio is 1. Click OK and click OK. You won't need to use the plot, so move the plot to the side. What really matters is this test, and you can see that it says F test. Right, the F method, and you have the p-value and the confidence interval. Test statistic is 1.12, F value 1.12. You see that we've got the exact same value here, and our p-value is 0.37, 0.37. Okay, and so based on that, we failed to reject. Test is inconclusive. Okay. So here's a fairly elaborate example that I want you to practice. If you can understand and go through the steps well, then you're in good shape. So in my example, we have hours spent studying per week that were reported by students in a class survey. Students who say they usually sit in the front were compared to students who say they usually should sit at the back. So for 99 students who reported that they usually sit in the front, the mean was 16.4 hours. Excuse me. 16.4 hours, with the standard deviation of 10.85 hours for the same group of students. For 94 students who sat at the back, the mean was 10.9 hours and a standard deviation of 8.41 hours. Both populations were normally distributed with the same population standard deviations. Assuming that, at a confidence level of 99%, first confirm if there is a difference in population variances or standard deviations, and then based on what you find, test for a difference in means. Okay, so first step, you have to test for a difference in variances. Notice that these are two different hypothesis tests. Okay, so first we're going to test for a difference in variances, and based on what you find, you want to test in difference in means. So let's do the whole thing in Minitab, one at a time. Okay, so we go to stat, basic statistics, two variance test. So first we're doing a two variance test, right? This is information from before. We're doing a two variance test. What do we have? We have sample size. One is 99 and the other one is 94. And the standard deviation for the 99 is 10.85. And the standard deviation for the 94 is 8.41. Okay, and we're checking if the two variances are equal or not. So again, you have the output, right? We don't really need the graph. So we're doing a test on two variances. Okay, we don't really need all that other information. What really is important is this output, right? F-test, 2 different degrees of freedom. The test statistic, 1.66, is your F statistic, and a p-value of 0.014. Okay, 0.014. So at a confidence level of 0.09, well, if confidence level is 0.09, that means alpha equals 0.01. And here, since our p-value equals 0.014, that means p-value is greater than alpha, which means we cannot reject H0. Okay, H0, that the two variances are equal to each other. Okay, are equal to each other. Okay, we cannot reject that. So we can assume, based on this test, that the two variances are equal to each other is true. Okay, since we cannot reject it. Cannot reject H0 because p-value is greater than alpha. Okay, and therefore, based on this first test, we're going to assume that the two variances are equal. We're going to have to do a test for difference in means. Right? So for doing a test for difference in means, what are my two options? A two-sample test or a pooled t-test. Right? Well, since we're assuming that the two variances are the same, we gotta have to use the pooled t-test. Okay, so let's just do that in Minitab again and find out the p-value and make a conclusion. So in Minitab, we go back to stat, basic statistics, two-sample t-test. Here we have it all summarized. Remove your old data. Our sample sizes are 99 and 94. Our sample means are 10.85 and nope, got that wrong. That was the standard deviation. The sample mean was 16.4 and 10.9, and the standard deviations was 10.85 and 8.41. Okay, we have to go to options because we're doing a pooled t, so you're gonna have to check off assume equal variances. Click OK and click OK. So based on that, we get a t statistic of 3.92 and our p-value of 0. Our pooled standard deviation value is 9.7386, but really the most important output that matters here is that our p-value is 0. Okay, so since p-value is 0, we reject H0, therefore mu1 is not equal to mu2. Okay, two different means that the are different. The people who sit at the back are different from people who sit at the front in terms of the average amount of time spent studying. So notice two different tests. Okay, this was a test on variance. So read your questions very carefully when you get it on the test. This is a test for difference in variance. This is a test for difference in means. Okay, and based on your output for the difference in variance, you could make a certain assumption about the variances, that they're equal. And using that, you decided to use a pooled t-test and then found the value for p-value, and that led to a conclusion. This is a good elaborate example that looks at two different hypothesis testing merged into one question. Okay, now we're going to finish up the chapter by talking about the final thing that's left, proportions. Okay, proportions. P1 and P2. Right, we're going to make hypothesis tests about P1 and P2, use sample P1 and P2 to learn about the difference in proportions. Okay, and so the standard deviation or the standard error in the difference in proportion is calculated as that. Okay, standard error. Okay, and therefore the difference in the proportions is where the middle is, and the spread, the standard error, is formulated as that. Okay, and based on that, we can construct a confidence interval. Okay, so difference in proportions plus or minus m, the margin of error. Margin of error is your z critical times the standard error. Okay, so that's your z critical times that standard error that we just saw using the sample values. And again, you have to make sure n times p is greater than 5 and n times 1 minus p is greater than 5. Okay, that means to check n1 times p1 greater than 5, and n2 times p2 is greater than 5, and then n1 times 1 minus p1 is greater than 5, and n2 times 1 minus p2 is greater than 5. All of these have to hold. Okay, that's your major assumption. All of them have to hold. And then you can use the confidence interval to compute the confidence interval. Okay. Okay, so if we were to look at an example, you're looking at sweat labels for apparel that's worn by women and men. Okay, and 63 out of 296 has a positive outcome, and 27 out of 251 has a positive outcome. Okay, so maybe they showed that, what is it? Label, want to calculate difference in proportion. Proportion of labeled users label. Okay, so 63 women out of 296 wear no sweat labels, and 27 out of 251 wear no sweat labels. And so we're trying to find out, is the proportion of females wearing no sweat labels different than the proportion of males? It's a valid question, right? So you can target your promotional activities differently. So you have to find out p hat, proportion of women and proportion of men. Again, these are hats because they're sample values. Right? 27 divided by 251 is 0.108, and 63 divided by 296 is 0.213. And then you have to find out the standard error. Okay, so this turns out to be square root of 0.213 times 1 minus 0.213 divided by 296 plus 0.108 times 1 minus 0.108 divided by 251. And when you equate that out, that turns out to be 0.031. Okay, and then to form the confidence interval, CI, that is going to be p hat 1 minus p hat 2 plus or minus z critical, right, times the standard error. And so this is 0.213 minus 0.108 plus or minus. Now let's formulate it for 95% confidence. So you know this is 1.96 times by what we just found out, 0.031. And that gives you the confidence interval when you equate it out. Okay. Similarly, if we were to do a hypothesis test, again, assuming that the assumption holds, we can find out our z-stat. Now, the only thing that changes in here, okay, in z-stat, we use what's called a pooled proportion to compute the standard error. So use pooled proportion to compute standard error. Okay, and that pooled proportion is nothing but x1 plus x2 divided by whole thing n1 plus n2. And then get z-stat from that equation and plug it in. Oh, that's a typo. It should say n1. Okay, n1 and n2. So let's look at an example. The same sweat example. Okay, you want to test for P1 equals to P2 and P1 not equals to P2. Our assumptions hold. Okay, if you multiply 296 by 213, you're going to get 63. If you multiply 251 by 101, you get 27. Both are bigger than 5. Right? Assumptions are okay. And the gap between these two is going to be the 1 minus p times n. That's also bigger than 5. And so the same here. So all our assumptions hold, all 4 of them. Now let's find out the pooled proportion. Okay, that's 63 plus 27 divided by 296 plus 251. So you're adding up the top, dividing by the total by the bottom. Okay, and that pooled proportion turns out to be 0.1645. Okay, and then we have to find z-stat. Okay, that is p hat 1 minus p hat 2 divided by, going back, pooled proportion times 1 minus pooled proportion. Okay, so square root pooled proportion times 1 minus pooled proportion. One over n1 plus 1 over n2. And that's just plug and chug. 0.213 minus 0.108 divided by square root of 0.16 times 1 minus 0.16, 1 over 296 plus 1 over 251. Okay, once you find out the z-stat, then you find p-value and make your conclusion. But why don't we look at how to do this through Minitab. Okay, now we're going to do a two proportions test in Minitab. So back to stats, basic statistics, and then we go to two proportions. Okay, we have it summarized, so it's much easier for us. It's all summarized. The number of events that we had was 63 for females, and the number of trials was 296. So always make sure the denominator is bigger. That's the total number of times something happened. So that's our sample size in 296. And 63 of them was positive. So the numerator is smaller, always. Okay? And then for men, you have 27 of them that were positive, that wore sweat glands, no sweat tags in their shirts, out of 251. Okay? Now, the little thing you have to be careful about is because we're using the Z distribution to approximate the proportions test, we go to options, okay, and we check this to say used pooled estimate for the proportion. But that's what we did, right? We used a pooled proportion in the standard error. Click OK, click OK. You found out the Z value 3.31 and the P value 0.001. Okay, so based on this turns out to be 3.31 and p-value 0.001. Right, 0.001 and 3.31. Okay, and so therefore reject H0, accept H1. P-value is less than alpha. So therefore, there is a difference in gender between usage of no sweat labels. Okay. All right. So then finally, this table summarizes again for you the comparisons that we have based on proportions. You can again compute Z critical with the values or the p-value with alpha. Okay. And in this class, we will use the pooled proportion as shown here, where pooled proportion is x1 plus x2. These are not bars, okay? These are not averages. Just the proportions, right, over n1 plus n2 to do this. Okay, well that brings a close to 2 sample tests. We've covered 2 sample Z, which hardly will be used. We've covered 2 sample T. We've covered pooled T. We've covered paired T. These were all on the means, right? A hypothesis test on mu1 equals to mu2 versus mu1 not equals to mu2. Then we did 2 variance test for H0 variance equals to each other. And them not equal to each other. And we did a 2 proportions test. Okay, so all these different tests we have now finished in terms of 2 sample tests. All right, that brings an end to this chapter. Again, make sure you're following along with your homeworks and your quizzes. If you have any questions, contact me at aroy.bgsu.edu.